Welcome back to our series on statistical methods. I'm Mark Ledbetter, and we are in the section for ANOVA and design of experiments. This is lecture 6, part 1, and we are starting one-factor experiments, also known as one-way ANOVA, and that is chapter 3 in our text. So let's get started. In the last chapter, we discussed hypothesis tests in detail, and then we looked at confidence intervals. In both cases, we were looking for the two-sample test. And so this is actually a one-way ANOVA with only two levels, or two levels of a factor. Okay, and we'll discuss that more. Here are the equations for the confidence interval. I had a question about the confidence interval here and about the alpha over 2. And so I want to quickly review that if this is t, and this is t alpha over 2, this is negative t alpha over 2, what this means is, by definition, the alpha over 2 is the area above the number t alpha over 2, whatever number that is, the critical value. So, and I need to undo my circle there. So here, this area is alpha over 2. So since it's symmetric, about 0, that means that negative t alpha over 2 tells me that this area down here is also alpha over 2. So that means that the area between is 1 minus alpha. Okay? And this is a 1 minus alpha percent confidence interval. That's what I shouldn't use that type of arrow. That's what we are calculating here. And this is where variances are equal, but we have to test for that. We can't just assume it. And this is where variances are not equal. And this is new, and it is the this formula that everyone loves is the Satterthwaite degrees of freedom. Okay, so this formula is much easier to use, but then we have to have S sub p, which is the square root of, let's see, n1 minus 1 s1 squared plus n2 minus 1 s2 squared, the pooled variance, the pooled standard deviation, n1 plus n2 minus 2. So both formulas have a little bit of calculation to them, but of course this degrees of freedom here is tedious to calculate, and I suggest you use a spreadsheet or something and do it by pieces, because it is very difficult to get this number right in the calculator. I sometimes have to do it 2 or 3 times, and once I've gotten the same number 2 or 3 times, then I'm comfortable that I've done it right in the calculator, just to let you know. All right. But in this class, luckily, you won't be calculating that manually. We'll let the computer do it for us. Okay. So let's start chapter 3. And again, this is a one-way analysis of variance. It's also called a one-factor analysis of variance. Analysis of variance is abbreviated here, and so the AN is from analysis, the O is from of, and the VA from variance. I don't know exactly how it got this abbreviation, but it did, and that's what we all use. Okay, so when there are more than 2 levels to a factor. Now, what is a factor? A factor is a variable. It's a variable with levels. Okay, so I can have, let's say we're going to use an example where we're talking about the power that goes into a process. And so power is measured in watts, and it is continuous. But what we're going to do is we're going to make it into factors, and that's what we have to have to deal with ANOVA, analysis of variance requires factors. And so even if we have a continuous variable, we're going to break it into levels. And so what we do with this power is we're going to break it into levels of 160 watts, 180 watts, 200 watts, and 220 watts. So we're only going to use these values, even though there's an infinite number of values we could use. To do an analysis of variance, each of the variables has to be made into factors which have levels. We chose 4 levels, or 4 treatment levels, or 4 levels of the factor here. It could be 2, it could be 3, however many you need for the experiment, or however many you think is reasonable for the experiment. All right. So I know that sometimes when we're teaching, we know what factors are and we fail to explain it. I want to make sure that we're on the same page from the start. So again, there's a lot of practical situations where we need more than 2 levels to be tested, and or there are several factors, it says, that are of simultaneous interest, and that's another way to look at it. So it's really a lot of the design of experiments is how we look at the experiment and how we arrange things and how we decide to test it. But that's jumping ahead. So we'll start with the very simple examples and build up to the more complex ones. So the analysis of variance is what we call an appropriate engine for these types of experiments. And ANOVA was developed by Fisher back in the early 1920s, and Fisher applied this to agricultural experiments for yield in the crops. So fertilizer, watering, all the different things that you could do to maybe improve the yield of a crop. And that's what he applied this to. And he was very practical when it came to this. And it's now, today, this book is about industrial type of experiments. So, of course, the author is going to tell you that it's extensively used today in industrial experiments. From my experience, I can tell you that is true. I've worked for several different manufacturers over my career, and we used design of experiments, ANOVA, whenever we needed to solve a very complex problem. And so it's widespread in industry these days. So here is an example. I will not read this to you. This is more information than you probably need to do this experiment. So if you'd like, please pause and read the slide. So this is about integrated circuit manufacturing, and wafers are made and they are then cut into tiny pieces that can be used for various different electrical purposes. And so this is going to be the wafer etching process, where we're going to etch something into the surface of the wafer. But before we do that, we put on a layer, a coating of some type of material, and then we etch something out of it. Maybe a pattern for a circuit, maybe a window for something. So there's a lot of different ways to look at this. And if you're interested, you can go to this video on YouTube and watch a 15-minute long video about wafer etching. It's very interesting. So I thought it was very well done. And I have personal experience with wafer production, glass wafer production, not silicon wafer production. And so the customers of my previous company did this process. So to me, this was very interesting. Okay, so we've got the gas supply. So you can use different types of gases. And up here it says such as tetrafluoromethane or hexafluoromethane. Those are 2 common gases that are used. And so some control panel to control the amount of gas. We have an RF generator here to supply the power, and the anode, it supplies the power to the anode. You have the wafer here, a cathode here, and then this valve and a vacuum pump. And I'm thinking, I don't know, but I'm thinking that the vacuum pump is used to hold the wafer into place. But it could be used for another purpose as well. It may be to evacuate everything but that gas from the atmosphere. So it's been a while since I've done that. All right. So again, if you're interested in seeing more about wafer etching, if you find that interesting, please look at this YouTube video. I thought it was well done. Okay. So we have an engineer, and she's interested in the relationship between the RF power setting and the etch rate, how fast this can etch something without defects. That's the key there. You can turn up the speed as much as you want, but you might end up with really poor quality. So you want to be able to do this faster with good quality. And that's not said, but it's understood by the engineering people. But maybe for us students who aren't familiar with this, we might not know that. So we want to determine the relationship between the etch rate and the power and specify the power setting that will give a desired target etch rate. Okay? So again, when we talk about desired, it's kind of hidden that we're talking about the quality level there. You know, the number of defects and maybe the cleanness of the line, no bleeding, no chipping out of the wafer, etc. So the response variable is going to be the etch rate. That's going to be Y. Okay? And she's limiting this to one gas. Okay? So I think this is hexafluoroethane. I'll say it right in a minute. And a gap, and that's the distance between the anode and the wafer. And so that's set. So these are not variables because they're fixed and set, and they're not going to look at anything else. They know that these are the things that we want to use. And so what she wants to test are the 4 levels of the RF power. Now again, this is a continuous variable, but we're breaking it up into just 4 settings. So these are either 4 equally spaced settings across the range of the power, or they're presets, or they're power levels that have been used in the past based on maybe other factors like the different gas, the different gap, etc. And she wants to test 5 wafers at each level of the RF power. So she's going to she chooses 4 levels of RF power. Again, here they are. And the experiment is replicated 5 times. So 5 wafers at each level of power. So the replications they're not the same wafer. They are different wafers, 5 different wafers at each of the 4 levels of power. Okay? So some of the terminology, I hope this helps. So here are the results, and we have the power here, and so we have the 4 different levels of power. And then for each level of power, here are the 5 observations. Then we've totaled that up, and we've taken the average of this, so we've divided this by 5, or n, if you will, and we've done that for each of the power levels here. Okay, so you're going to see another slide in a minute with symbols here to represent these values, and the terminology, the symbology is very important. Okay, so now what they've done is they've done box plots, and we'll learn how to do these box plots. I've already shown you how to do this for 2 levels. It's very easy to do it for 4 levels if the data's in the right configuration. And so by putting all 4 box plots on the same chart, we can see that the etch rate generally increases as we increase the power, right? And then this is, they call it a scatter diagram, but it's also a strip chart or a dot plot. Okay, but you can call it a scatter plot, but it's actually 4 scatter plots on one, but it's linear. It's not really, it's not so much of a, I don't consider this much of a scatter plot, but I guess you could technically say that it is. So we have etch rate in the y-axis. That's our response. our input variable is the power at these 4 different levels. And again, you see that generally speaking, as the power increases, the etch rate increases. Okay? So these these graphical analyses are very important. And sometimes they clue us in to something that's occurring that we need to know, and that may point out that we're violating an assumption of the test, so we can't use the test we wanted to use. So never skip the exploratory graphical analysis. It's always extremely important. Okay? So here's what she wants to know. Does changing the power change the mean etch rate? And by looking at those plots, we would tend to say yes. But we need to do this scientifically and use statistics to have a confidence level that we can say yes or no. Okay? And is there an optimal level of power? That's the second thing that we want to do. If changing the power changes the mean etch rate, then we would ask the question, what's the optimum level for the power to get the best etch rate? And we want to have an objective way to answer the questions, and the t-test doesn't really apply here. There's more than 2 factor levels, okay? And so we could do this, but we won't, and I will talk about that a little later. So now here's the same experiment over again, but with symbols. So we have our treatment level, which is the power in this, and so the first level, the second level, up to the 8th level. So there's I equals 1 up to A are the treatment levels or treatments. It's either treatments, different treatments, or different treatment levels, or the levels of one treatment. So in this case, we have one treatment, which is the power, and we have 4 different levels. Now, the first observation in the first treatment level, so this is Yij, and so I is the treatment, I'm going to abbreviate that, TRT, treatment level, and J is the observation. So this says the observation in treatment level 1 is the first observation. The first observation, sorry, that's not big enough. So let me zoom in. So the first observation in the first treatment level. You'll notice the 1 stays the same across here all the way to N. And so we have the second observation in that treatment level up to the nth observation in that treatment level. And we're dealing with a balanced design here where each of the treatment levels have the same number of observations. We don't have to do that, but we'll find out that it's definitely one of the better situations when we can do that, that we increase the power, and so it makes it a better test by doing this. Okay. And the calculations are a little easier if you're doing them by hand, but we have computers, so that's not too big of a consideration. Okay. Now, we go to the second level here. And so on the second level, we now have the first observation in the second level, the second observation in the second level, up to the nth observation in the second level. And now let's look at the totals. So when I add up all of these n values here in the second level, I represent that total as y sub, and that sub meaning subscript, sub 2 dot. And the dot means we summed across that index. And the index in this case is J. So J is our observation. We summed across the observations here, and that gives us Y2 dot. So that's a sum or total. And then when we average that, we call it Y2 dot bar. So yes, the period is there, the dot is there, okay? And in the first treatment level, it would be Y1 dot bar. So, and usually we say the subscripts before the what's on top. So if it was hat, Y1 dot hat. We say the hat last, we say the bar last. That's typically how we do it, but no one's going to be critiquing how you say it here, at least. So in industry they might, but yes. So then this is missing a dot, so that's YA dot. And then we see YA dot bar, whoops, over here. And the line is just to show that we're totaling it, okay? That line is just to show that we're going to add these. Okay, so Y dot dot is the sum of all the observations. And there are A times N observations in this model because we have A levels, and in each of the levels there are N observations, so A times N. And so when we take Y dot dot and divide it by A times N, the total number of observations in the model, we get this. And this is equal to YA dot divided by N, because in this row, there are N observations. Okay? All right. So I hope that helps explain how we calculate this. And the notation is important to understand. I don't want to just brush through it because students get very confused the first time they see this if it's not taken slowly enough and clearly enough. So in general, there will be A levels of the factor. Now we're talking about the one-way ANOVA or one-factor experiment. Or A treatments. Again, these are two different things. So there could be one setting of power and one setting of we could be trying one setting for power here, and we could be setting one setting for gas, and then one setting for something different. I guess gas is not a good one, but some other variable that we wanted to change. But if we were keeping everything else the same and just changing the different treatment, let's say it was different gases. So instead of power, you were holding the power the same, and then you do one of the gases here, another gas here. Well, you could still say that that's different treatments, or you could say that that's different levels of the treatment called gas. Okay, so. And in replicates, that's how many observations are in each treatment level. That's how many times you repeat the experiment with the same values, okay, with the same settings. Oops. Number of times new units, experimental units, are run with identical settings. Okay, so it's a repeat of the same trial over and over again. That's a replicate. They have to be run in random order. If they're not run in random order, then you may have some dependency, and dependency will destroy the results of your test. They'll be worthless without independence, this type of test. Okay? And if you have A levels of the factor or A treatments and N replicates, and they're run in random order, then you have a completely randomized design called a CRD. So completely randomized design. Let's clean up a little bit. And so we're going to consider the first case, which is fixed effects, and later in this chapter we'll talk about random effects. I don't want to talk about them at the same time right now because I think it's better for you to learn one and then come back and see how the other is different. But before you have gained proficiency in all the notation and all the calculations and all the terminology, I think it's too confusing to talk about both at once. So the objective is to test the hypothesis about the equality of the A treatment means. So there's A different treatment means, and those means, again, we'll clean up my marking mess over here. These are the treatment means. Okay? So we want to test whether they're all the same, and that makes sense. Is there a different mean response or in this case, mean etch rate? Is there a different average or mean etch rate for the first level of power versus the second level of power versus the third or the fourth? And these are the averages that we want to compare. Okay. So, again, why would we want to do a one-way fixed effects ANOVA? We want to compare 3 or more means or treatments in a single experiment. Okay, the means of the treatment, okay, or treatment levels. Factors, again, are levels of a variable. So again, power is continuous, but we're choosing 4 settings, just 4 values, and those are the levels of that factor. Okay. Fixed effects means that we're going to predetermine, we're going to in advance set the levels of the factors, and we're going to do it manually. In other words, we're going to say, this is the value of power I want. I want to test these 4 values of power. I'm not going to choose them randomly. That's the key. I'm predetermining, presetting these levels. Okay. Now we could compare 2 of these at a time. Instead of using ANOVA, we could say, I'm going to use a 2-sample t-test. I'm going to compare these 2. Then I'm going to compare the first and the third. Then the first and the fourth. Then the second and the third. Then the second and the fourth. And finally, the third and the fourth. That's a lot of 2-sample t-tests. So why would we not want to do this? One, the very first thing is not what I just went over. It inflates the type 1 error. Whoops. Alpha. It makes it bigger than what we want. It makes the actual bigger than alpha. So that's inflating it, making it bigger, blowing it up, so to speak. Okay? The second thing is that it's not efficient. So that's what we talked about. Having to do 2 at a time is really not efficient. So 4 choose 2. So let's see, 1, 2, 3, 4, 5, 6. Yeah. So the hypothesis statement. So again, we're testing that the means of the different treatment levels are the same. So the null hypothesis is easy to write if we're going to use mu. Okay. And then we have to say versus if any of them are different. So any 2 means are different. And so how we write that is mu j not equal to mu k for j not equal to k. What in the world am I saying? What I'm saying is we're not going to say that mu1 is not equal to mu1. That doesn't make any sense. So that's why we're saying that j is not equal to k. All right. So any means that are not equal to each other, that are not the same mean, because obviously mu1 is equal to mu1. But we know that and we don't care about that. What we care about is mu1 not equal to mu2, or mu1 not equal to mu3, or mu1 not equal to mu4, or mu2 not equal to mu3, or mu2 not equal to mu4, or mu3 not equal to mu4. But we don't want to write all this out. So this is j, this is k. So we will say that the null hypothesis is not true if any of the means are not the same. So in this simple case where we only have 4 levels, we can write it out with 6 possibilities, but we wouldn't want to, right? So this is an efficient way of writing the alternative hypothesis that any 2 means are not equal. So this was K. Okay. All right. Now, because we're not satisfied with just one way of writing things, we're going to have more than one way of writing these models. So we're going to talk about models, because if you remember, we have to say the null hypothesis versus the alternative. We're testing the hypothesis, or we're testing the null hypothesis versus the alternative hypothesis in the model. And so now we have to configure the model. Okay? So the first model is called the means model because we're going to use mu I. And we're going to say mu I, which is the mean of the ith treatment level plus the error of this individual observation. So for the yi jth, so the jth observation in the ith treatment mean, that is equal to the sum of the mean of the ith treatment level plus random error. Okay? So that's epsilon ij. And so we have I equals 1 to A, and j equals 1 up to n. And these are very important. You have to tell us what they are. And now, where yij is the jth observation in the ith treatment, TRT is treatment for me, level. Okay? Mu I is the mean of the ith treatment level. And epsilon ij is the random error associated with the jth observation in the ith treatment level. OVL is also level. But it kind of looks like absolute value of V, so maybe I won't do that. Okay? But, of course, we can't be satisfied with that, so we want to look at this a different way. And so what we're going to do is we want to look at this in terms, we may want to look at this in terms of the overall mean, mu. So the overall mean of the entire, the entire experiment, okay? So we could say that this is equal to mu plus tau I plus epsilon ij, but these have to be the same thing. These are the same thing. So we have a relationship between tau and mu I, and tau is equal to mu I minus mu. So this is the treatment mean minus the overall mean, or sometimes it's called the grand mean. I don't, but other people do. And so, and then of course, we've already defined what yij is and mu I and epsilon ij. So I'm not going to repeat that. It's the same thing. Okay. But again, we may want to look at it a different way and use regression. So there's a regression model that we're going to go over as well, but we'll do that later. Now, with each of these models, there are assumptions. And if these assumptions are violated, then your results don't mean anything. They may be right or they may be wrong. You don't know. So we have to be careful and make sure that we understand the assumptions. And if we violate the assumptions, we have to know whether or not we can, if we can proceed, or if we need to do something different, we need to start over. Okay? So we're going to start with the means model. Now, the assumptions are basically the same for both models. Just some of the assumptions are written in a different way. They're expressed differently. And so depending on which model you use will determine which of these assumptions you're going to write down each time, because each time you do this, I'm going to require that you write the assumptions to make sure that you understand these really, really important things that you have to check. So within each treatment level, we consider each treatment level a separate population. So every one of those A treatment levels is its own population. And each of those populations have to be normally distributed. Now, if these are run randomly, then the observations within random sample means observations within treatment level are independent. Okay? But this is saying that the populations of each treatment level are independent to each other. So, to each other treatment levels. Okay, so each treatment level is independent of the other treatment levels, and we already have that the observations within each treatment level are independent. So this means that all the observations in the whole experiment are independent. Okay, and this next one is very important. It says that all of the variances are identical. So that for each of the treatment levels, the amount of variation in treatment level 1 is the same as the amount of variation in treatment level 2, ... same as the amount of variation in treatment level A. So all the variances, because remember, each of these treatment levels is a population, and so the variance of each of these treatment levels has to be identical, and we just write that as sigma squared. Okay? And so, putting all of this together, we have that Yij is normally independently distributed with mean mu I and variance sigma squared. It's clear that it has variance sigma squared. It's not clear how do we get expected value mu I. I mean, you might say it's clear, but let's look at this. Let's do a very brief proof. E of expected value of Yij is equal to the expected value of mu I plus epsilon ij. Now, expectation is linear, so this is expectation of mu I plus the expectation of epsilon ij. This is a constant, mu is a constant, so this is just mu I, and we set up here that epsilon, let's see, did we say it somewhere? No, we need to. It is normally distributed with mean 0 and variance sigma squared. Okay, so that means that the expected value of this has to be, oops, that's not right, has to be 0. So the expected value of Yij is simply mu I plus the expected value of the error 0. It makes sense intuitively that the expected value of this random error is 0 when we're talking about it being a deviation from the mean, right? So some of them are above, some of them are below, and when you add up all of these errors, all of these differences of these observations, which are randomly above, randomly below the mean, they have to sum up to zeros. Those errors have to sum up to zeros, or else that's not the mean. Okay? And this is the reason that people like this effects model, is because tau I is the difference between mu I and the overall mean. Okay? And so we're looking at how different is mu I from mu. And so we have a measure of that, and people like to estimate that. How far away from the overall mean is each treatment mean? And are those treatment means statistically significantly different from each other? Okay, so now we have the effects model. Again, we have normally distributed, independent between treatments. Okay, they all have the same variance. This is treatment levels. And so then we have that the sum of the effects, these tau I is called the treatment effect. The effect of that ith treatment. So the sum of those all has to be equal to 0. Okay? So this is pretty easy to show. So the sum from I equals 1 to A of tau I is equal to, I substitute in for tau I, that's mu I minus mu. I equals 1 to A. I have a subtraction and I'm summing across it. I can distribute the summation. So I equals 1 to A. And so mu I is simply equal to, so this is the sum of mu I. So we have an I there as an index, so we can't get rid of that. But we don't have an index for mu here, the overall mean. And so this is A times mu, okay? And this says if this is equal to 0, then we solve for, we're going to solve for mu. Then we have sum of mu I equals A mu. We've added A mu to both sides of the equation. And then we can divide both sides by A. We end up with 1 over A sum of mu I from I equals 1 to A, which is, I'm sorry, I left off the first part, which is mu, implies mu is equal to, the overall mean is equal to the average of the individual treatment means, which is true, has to be true, if the sample sizes of each treatment level are equal. Okay? So think about that. And so then, since we have that the sum of tau I is equal to 0, then Yij has to have a normally independently distributed mu plus tau I mean and variance sigma squared. So because E of Yij in this model is equal to E of mu plus tau I plus epsilon ij, which is equal to E of mu, which is just mu, plus E of tau I, which is 0, plus E of epsilon ij, which is 0. Oh, I'm sorry, this is not 0. This is a constant. It's not the sum of. This is tau I. And so we have mu plus tau I. I was thinking the sum of tau, but no. Okay. So we will stop here in this video. I think that's enough for one day. This is a lot to take in. So please make sure that if you have questions that you email me. If you can't wait until office hours, but also please make sure you come to virtual office hours. Remember, it is a requirement for your grade, 10%. So it's an easy requirement to meet. You're free during the class time because it's listed as synchronous, so you shouldn't have anything else that interferes with it. And it is 10% of your grade. So please come to office hours. And if you can't make it, if you need help before then by all means email me. I'll get back to you as soon as possible. Also, please take care of yourself and stay safe so that we can see you next time.